Let's take a look at Lewis structures. And Lewis structures are the way that scientists can draw a molecular compound or two nonmetals when they join together. Because we've talked about how they share electrons. So if we take a look at H2O, for example, which is water molecule, it's the essential molecule for life. It has two hydrogen and one oxygen atoms. If we look at the periodic table, we can determine that oxygen is in group 6. So drawing the individual Lewis structure of oxygen would give us 6 dots around it. And hydrogen would have 1 dot because it's in group 1. Same thing with the other hydrogen. So when you draw a Lewis structure, you have to individually draw the Lewis structure of each of the elements in the compound. And I made these different colors, one blue and one red, so that you can see how when they get closer together, you should be able to see the overlap of the shared electrons. For example, the hydrogens. In order for hydrogen to be stable, it wants 2 electrons in its outer shell. And if you look at the circles, it has one of the electrons from the hydrogen and one from the oxygen. So it does have 2 when it shares the electrons. We can also look at oxygen. And if we look at oxygen's total number of electrons, now it has 8. It has 6 from itself and then the 2 that it shares from the hydrogen. That's how it's shared. Now, when we draw it, we don't draw it like this and we don't do the circles, but normally you'll show Lewis structures where each bonded pair is represented by a line. So since hydrogen and oxygen are sharing a pair of electrons, we just draw a line. And then you can see the 2 dots on the top and the 2 dots on the bottom. Those are called lone pairs because it's a pair of electrons. So when we count this H2O, we can count that there's 2, 4, 6, 8 electrons total. Again, because each line counts as one. Let's take a look at one more example that way. Let's look at CH4. This is methane. We can put carbon in the center. Carbon has 4 dots to it because it's in group 4 from the periodic table. And hydrogen has 1 dot each. Hydrogen wants 2 electrons to be stable, and carbon wants 8 electrons to be stable. So when we look at it this way, all of the hydrogens are filled with their outer shell. And then if we look at the carbon is filled in its outer shell. And this is how molecular bonding or covalent bonding, this is how it works. Nonmetals will share electrons with each other. It's not as strong as ionic bonding because there's not the opposite charged particles attracted to each other. And again, anytime you have a bonded pair, then you would draw a line as opposed to the dots, and each line counts as 2 electrons. So hopefully that helps you understand and visualize what is meant by shared electrons with the different colors. But when we actually draw Lewis structures, it's a little bit simpler than that. You do have to know a couple of things. You need to be able to look at the periodic table and determine the total number of valence electrons. The valence electrons are the amount of electrons in the outer shell, and that information is gained from just looking at what column it's in the periodic table. For example, oxygen. Oxygen is in group 6, so it has 6 valence electrons. In this compound, we only have 1 of them, so there's 6 valence electrons for oxygen. Hydrogen is in group 1, so it has 1 valence electron, but we have 2 hydrogens. So we have to look at the total amount. And when you have the 6 valence electrons for the oxygen plus the 2 total for the hydrogen, your Lewis structure needs to have 8 valence electrons. Now there's some simple rules to know which element to put in the middle and which ones to put first, but the general thing to know and realize is that hydrogen is never central. And you'll see this after we go over a couple of examples. So start off by putting the element that's not hydrogen in the middle, which is oxygen. And then the next thing you want to do is put your hydrogens around it. And then you want to connect it with single bonds. Each line represents a bond. It represents 2 electrons. And you know that oxygen is going to have 8 valence electrons because that's the octet rule. The octet rule is all atoms try to get 8 valence electrons, and we know that hydrogen is an exception. It only gets 2 valence electrons. So when I add the lone pairs and I look at it, picture the circles from the other picture, hydrogen has a full outer shell and oxygen has a full outer shell. So now what we have to do is count how many total electrons we have. We're trying to get 8. We have 2, 4, 6, 8. Oh, it's awesome. People are clapping. It's exciting because we got the amount that we were looking for. So we know this is a good Lewis structure because it shows the 8 total valence electrons we were expecting. Lewis structures is something that you just have to practice multiple times and you'll get really good at it. And it's kind of fun. It's almost like solving a puzzle. Let's look at the second example that we used with the Venn diagram bubbles. Methane. Again, hydrogen will not be in the middle. So let's put carbon in the middle. Let's surround it by the hydrogens. Let's add the bonds. Now, looking at this, we don't have any room to put any more lone pair. So this is the maximum amount that we can have. And each hydrogen atom has 2, and carbon has 8. So when we count it, we have, and going back up, let me backtrack just a second. Carbon is in group 4, so it has 4 valence electrons, and hydrogen is in group 1, but we have 4 of them total. So we're looking to get 8 valence electrons. And we have 2, 4, 6, clapping, yay! We have 8 valence electrons for this one. So we did this one correct as well. Another example would be determining the total number of valence electrons for NH3. So again, H's won't be in the center. Nitrogen is in group 5 from the periodic table, so it has 5 valence electrons. Hydrogen has 1 valence electron, and there's 3 total. So again, we're going to look for 8 total valence electrons. It won't always be 8, but we're going to start off with these simple examples. Remember, H never goes in the middle, so we put N as the central atom. We surround it by our 3 H's. We draw our single bonds. Now when we look at this, we see that each hydrogen is filled completely, but the nitrogen right now only has 6, and we know it can get 8. That's where we draw that last set of lone pair. So now when we count these, we get 2, 4, 6, 8. Outstanding. So the first few we've done were pretty easy. Let's take a look at another one. We have PCl3. P is in group 5. H is in group 1. There's a typo there. It should say Cl. So Cl has 1 valence electron, and we have 3 of them. So it should be 8 total valence electrons. If you have multiple elements, for example, when we had multiple H's, it never was in the center. If you have multiple Cl's or multiple F's or multiple Br's, you want to put the thing that you have a lot of around the outside of the central atom. So we're going to start with P in the center for this one. So when we start with P in the center, we put the Cl's on the outside. We draw the bonds. We know that P should have 8 total, so we have to add that extra set of lone pair. And this one is set up, yay! Just like the example before, where we have 8 total electrons, and that's what we were looking for. Now, one thing I said is it's not always going to be that simple. You're not always going to just have 8 like the first few examples. For example, for NF3, N has 5 valence electrons because it's in group 5 of the periodic table. Fluorine has 7 valence electrons because it's in group 7. So when we look at the total number, there's 3 fluorines, so that's 21 total. So if we look at the total amount, it is 26 valence electrons. So when we draw this, we should have N, F, F. We draw the single bonds, and this is where it gets a little bit different. Each of the fluorine atoms needs 8 total valence electrons, and the nitrogen also needs 8 total valence electrons. And now that I think about it, when I think about the last example was chlorine. Chlorine should have been set up the same way as this one, because chlorine is also in group 7. So the last one, hopefully it didn't confuse you too much, but the hydrogens all have 2 valence electrons in their outer shell, and all of those examples were the same. But chlorine and fluorine and anything else in group 7, they want 8 valence electrons. So what we do is we have to put the lone pair around everything, because each of these atoms needs 8 total electrons. So just picture this as a Cl for the last example. Now we do the same thing we did before and we count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Yay! So the rules are still the same. You draw they call it a skeleton structure of just the element symbols, and then you connect the symbols with single bonds, and then you add lone pairs until everything satisfies the octet rule. Or if it's hydrogen, it only gets 2 electrons. So that was an example of one that's a little bit more difficult. When we look at SO3, sulfur's in group 6, so it has 6 valence electrons. Oxygen is in group 6 also, but there's 3 of them total. So the total number of valence electrons for this one would be 24. S is in the center. We surround it by the oxygens. Draw the single bonds. Add lone pairs until the octet rule is satisfied for each element. And when we look at it, every oxygen has 8 and sulfur has 8. And then we count it up. 10, 12, 14, 16, 18, 20, 22, 24. Oh no. So this time we had too many valence electrons. We counted 26, but we're only looking for 24. When this happens, it's a quick fix, but what you need to do is you need to add a double bond, and I put it right there above the 6, see? Right there. Ooh. Add a double bond, and you can add it to any of the oxygens. When you add a double bond, you have to get rid of a set of lone pairs from each of the atom that you added that double bond to. So let's do it again. So between the oxygen and the sulfur, we got rid of one of the lone pairs from each because they're sharing another set. Right? And then every time you add a double bond or a triple bond, which I'll show you an example of in a minute, every time you add a bond and you get rid of a lone pair, it reduces the total number of valence electrons by 2. So if you had 4 more than you needed, then you would add 2 sets of bonds. Right? And I'll show you that in the examples. But let's go through and count and see if we did it right. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Yay! So whenever you have more valence electrons than you need, you're going to see an example of multiple bonds. Let's look at CO2. Carbon is in group 4. Excuse me. Carbon's in group 4. It has 4 valence electrons. Oxygen is in group 6. We have 2 oxygens. So the total number of valence electrons is 16. Carbon's in the middle. The oxygens are on the outside. We draw the single bonds. and then we put our lone pair in. When we count these electrons, we'll see that we got too many. We had 20 valence electrons and we only wanted 16. As I said in the last example, every time you add a bond, it's going to reduce the total number by 2. So we need to add 2 bonds to this one. Whenever we add a bond, we get rid of a lone pair. See, I got rid of the carbons and the oxygens, and another one from carbon and another one from the other oxygen. And then I can add another bond. So every time you draw a line between the two, you need to erase or cross out a set of lone pairs from each one. Then when we count it up, we get 2, 4, 6, 8. Who do we appreciate? Mr. Brand. Yeah. 10, 12, 14. Yay, 16. So that's another example of multiple bonds. N2. Oh, this one will be easy. There's only 2 elements. Awesome. So nitrogen is in group 5, so it has 5 valence electrons. We have 2 of them, so we're looking for 10 total. Put our nitrogen, put our other nitrogen, draw the single bond, add the lone pair, and then count. 6, 8, 10, 12. Whoa! Uh-oh. I thought that one was supposed to be easy. Well, we can fix it pretty quickly. We have 14 total. We only want 10. So that means we have to add 2 bonds somewhere. There's only one place to add the bonds. Every time you add a bond, you have to get rid of 2 sets of lone pairs, 1 from each element. So that's why all 4 of these dropped off, because I'm going to add 2 more bonds. Let's do that again. So in order to add a bond, you have to get rid of a lone pair from each element. And we know we're going to add 2. So I got rid of the 2 sets of lone pairs and added the 2 bonds. And then when we count, we get, woohoo! Sweet! We get exactly what we needed. Last example. All right, HCN. There's only 3 elements. They're all nonmetals, so we know it's drawing Lewis structures for it. Hydrogen has 1, carbon has 4, nitrogen has 5. This one's similar to the last one. So we put C in the center. You know how I said if you have multiple atoms, you put that around the outside? If you ever have carbon, carbon will always be the central atom. So always put carbon in the center. So for this one, we put the C in the center, we draw the single bonds, and then we draw the dots. Remember, a common mistake is people will put dots around the hydrogen, but hydrogen only gets 2 total, because that is a full stable outer shell for hydrogen. Now if we look at this, the rest of them have 8 total. So when we count, we already know this is going to be way too many. Whoa. Again, we have 14. We only want 10. So we have 4 more than we need. So we need to reduce the total amount by 4 by adding 2 extra bonds. So what we're going to do, just like we did before, we need to get rid of 2 sets of lone pairs, and we're going to add 2 bonds. Then when we count, 6, 8, yay! Now that we made it through all the examples, hopefully you have a basic understanding of it, but you're never going to be good at it until you practice it. We're going to spend a lot of time in class practicing these and going over these, and you'll get really good at it, and I'm sure you'll enjoy how to do it. Until then, here's a link on here, and the link will take you to somewhere on Google. I just typed in practice Lewis structures and a lot came up. But I'll give you some samples to try, and remember, if you're not part of the solution, then you're part of the problem. We'll see you guys tomorrow.